Hello, and welcome to the Clean Solutions webinar, Additive Interference in Laser Particle Counting, What is Causing It, Analytical and Filtration Application Issues that Cause It, and Methods to Deal with It with some real-world examples. My name is Jim Doyle. I'm an engineer at Donaldson in the Clean Solutions group. I'd like to start off this presentation with an image to get in the right mindset to understand what the issue we're trying to describe and explain. And this is a good corollary to it. Here's an image of a ship, or maybe some ships. You can see there's something out there in the water, and you can tell there's maybe one, maybe two, perhaps more out beyond what you can see there. But there's something in the way of giving you an accurate idea of what's going on out in the distance there in this image. And I want everybody to keep that in mind as we go through this presentation. So the objectives for today are to recognize the things that contribute to falsely high particle counts in oils, understand the impact of this issue in assessing real-time filter performance, be able to visualize real system debris types and distributions in oils and fluids, and learn how to more accurately assess system cleanliness, debris types, wear, and damage. So which of these two samples here is cleaner? I've taken a couple of different fluids, filtered a volume of it through a membrane patch, and I'm looking at what I see that was filtered out from the oil sample. It's fairly obvious that these are not the same level of contamination of fluid. But what if your oil analysis can't see the difference? That's a real challenge, and it becomes a very confusing issue for people. And that's what we'd like to discuss here. So here's what you would typically get if you took an oil sample of a new fluid you were taking into your facility or going to be using in equipment and send it out for oil analysis. This is a brand new lubricant oil analysis sent out to a typical lab. You'll notice there's some important categories of analysis here. First one being wear metals. This would be what things that would likely come off of components that are wearing in an operating system. You'll notice there are no wear metals present in this sample. They're all zeros. That whole category from iron to vanadium there is all zeros. There's another category called multi-source metals. These can be parts of the additive package, or they might be present in certain applications in service. And you can see there's no components there that have any real levels to speak of. But you'll notice the particle count down at the bottom is highlighted in red, and it's flagged as a critical level. And it's reading 22, 21, 15, a very high particle count, meaning this is a severely contaminated fluid, and it should be possibly rejected. And there doesn't seem to be much in the sample. There is one thing that's noted that's not part of the additive package over on the far right, and that is listed in the contaminant metals section, and it's silicon. Now, silicon could be a contaminant. It could be sand, it could be glass fibers, some other types of granular filtration media used in the refining process. But it is also now extremely common as a component of the actual additive package. It had to be listed somewhere on this analysis, and traditionally it was listed, silicon was listed as a contaminant. But now it is in a wide range of fluids intentionally, and it's not in there as sand or glass fibers. It's a silicone-based material that's an additive package component for anti-foaming performance. So here's a scanning electron microscope of an oil that contains this additive package, this silicone anti-foam. And you'll see a whole bunch of small gray spheres. You'll see we're at a 450x magnification here, so a bit more than you can see with a regular light microscope. But you can see there's just a ton of these little gray spheres visible. They're all over the patch there. Those are the anti-foam additive. They help break up air bubbles in the fluid and let air out of the oil quicker so that it doesn't cavitate when it goes back through the system. The particles that are now circled in red are actually hard particles that will do damage to your system. They're hard debris particles, and when they go through tight tolerances, they do damage. They wear and gouge out surfaces and do all sorts of damage. And those are what you're actually concerned about removing with a filter. Those are the parts that can actually do damage. Those are what are supposed to be counted to make up an ISO code. And we'll get a little further into the description of what an ISO code is, but just keep in mind that that is what we're trying to count. Those hard particles that can actually wreck components in your operating system. So I want you to think back again about the ship in the water there and what was in the way, and there was a lot of fog in the way, and fog is a bunch of small round clear spheres, and you can't see the ship out beyond them. So think of the silicone antifoam as the fog in that situation, and think of the red particles as the ships. That's what you're actually trying to count, is count the ships. And there's too many little round clear silicone spheres in the way. You're seeing the additive components by the thousands and just a handful of hard particles that you're trying to characterize. So again, how many ships do you see out there, and just what is in the way? There are no large particles in the way of being able to see that ship. There's just a ton of small clear spheres floating around in the air that makes it so you cannot see that ship. And that's an example of what we're trying to understand. So I mentioned we were going to cover what is the definition of clean or the ISO cleanliness code of a fluid. So the ISO code is nothing more than a method for coding the level of contamination by solid particles. It is a description, and all it is defining the concentration and distribution of different sized particles in a fluid. Large particles do damage to gearboxes and gears and things like that, and the higher pressure hydraulic systems are sensitive to smaller particles. So there's 3 different size ranges there to give you an idea of how many really big particles and how much small debris is in the system, as that's what can do damage to higher pressure and tighter tolerance components. So the numbers that you get in an ISO code are nothing more than a shorthand way to describe the number of particles in a sample of fluid. Let's take a look at an ISO 16 on the code chart on the left side of these 3 columns of numbers. An ISO 16 is 32,000 to 64,000 particles. So it's not an exact description. It gives you a range of particles. It's not an exact, the 16 isn't an exact description of number of particles. It's covering that range of 32,000 to 64,000. If you have twice as much debris as that, you're at an ISO code of 17. You have 64,000 to 130,000 particles of a certain size and larger. So we described the particles as we showed before of 14 microns and larger, 6 microns and larger, and 4 microns and larger. The first number in that code of a 4, 6, and 14 range is always the largest, and you have less and less as you count only the larger particles from there. And we'll cover that again. So the way that you can assess those numbers, there's two recognized methods for doing that in fluid analysis. The first one is actually using your own eyes. It's called a manual patch kit, and you pass a known volume of fluid through a filter patch. You can see that little funnel there. You pour the fluid in the funnel and you suck it through there with the pump and rinse off the oil with some solvent and then look at it with a microscope. A very direct way to look at the debris. You can see different types of debris, different shapes and sizes, and get a good idea of what the distribution of the particles are. That is it's the old-fashioned way, but it is by far the most direct way to look at what the debris in a sample is. The next method is called the machine particle count, and this is what is done at every oil analysis lab in the industry. They will run a machine particle count. It does a similar thing. It passes a set volume of fluid through a flow cell that has a laser shining across it, and it sizes anything that obscures the laser beam. It sizes them and determines the shape and totals them up for that volume of fluid, and it gives you a number. Here's a pretty typical bottle sampler, a very functional and usable piece of equipment. It's very handy, as provided you know that it's reading properly. And it gives you a readout of different size particle ranges. You can see 4, 5, 6, 7, all the way up to 40 micron particles there, a cumulative total. And it gives you the ISO code at the bottom there of those particles that it counted. It says it's an ISO 232219. That 23 is the 23 corresponds to the number of 4 micron particles and larger in the fluid. The 22 corresponds to 6 micron and larger particles in the fluid, and the 19 is the 14 micron and larger particles in the fluid. And that's what you're determining with both of these methods. So again, we'll go back to the ISO code list here, and just to give you an idea of how much debris it actually takes to make up some of these levels of cleanliness. I sort of mentioned an ISO 16 as a common target. That's a cleanliness code for hydraulic systems, and that's 32,000 to 64,000 particles, 4 micron and larger in a system. You can see that's just taking a fraction of a milligram per liter of debris, 0.16 to 0.32 milligrams per liter of debris to contaminate a sample of that level. You know, you're talking 1 to 3/10 of a milligram per liter. To go up to a 23, like we saw in that sample there from the particle counter readout, you're talking 20 to 40 milligrams per liter. So it goes up quickly as you go up this chart. The number of particles and the milligrams of debris it takes to contaminate that level goes up quickly. So keep that in mind as we continue to look at some examples of this. The way that the patch kit and visual counting example works, you're looking at the sample through a microscope, and you're simply counting the number of total particles you can see, and then sizing some of them to get an idea of the 6 micron and larger and the 14 micron and larger samples in there. And it's just simple math to go from the ISO code and a known volume of fluid on a known area of patch and count the particles to relate back to the ISO code number that it means. So a very direct means of measuring. To give a visual representation of what that kind of looks like and the types of targets that fluids need to be at, cleanliness targets they need to be at. Here's a range of contamination from clean enough for very high pressure applications in ISO 151210 or 161413. That's many hydraulic systems are specified to be maintained in that range. You can see there's very few particles visible under the microscope there. Gearboxes and a little more tolerant of debris applications, 181613 there. Second from the right is the target for those types of applications, but it is routine to see fluids much dirtier than that and contaminated with all sorts of things. You can see in the ISO 2018-13 sample, there's a bunch of fibers in there. There's soft contaminants in some of these. In the ISO 22-2117, there's some soft contaminants. You can see if you see a lot of particles through a microscope, you can say, okay, that fluid is very dirty. If you don't see a lot of particles visually through the microscope, it's a clean fluid. And if the machine particle count is high, you know you're having this kind of an issue. So now to just step through some examples of what happens if you have a straight fluid without any of these interference issues, this analytical issue that causes a machine laser particle count to be high. This is a straight hydraulic fluid with no anti-foam additive package in it whatsoever. It machine counts very clean, and visually you can see there are very few particles visible. Visually the number agrees very well with the machine particle count. And with some debris added to it, you can see it's gotten dirtier. The machine count goes up. Visually, there's quite a few particles there. Filter it back out, and we go back down to a very clean sample. The machine agrees that it's very clean, and visually there's very few particles. That's the way things are supposed to act, and they do, provided you don't have any of this anti-foam additive package in your oil sample. It's common in virtually all mobile fluids now, and some stationary hydraulic applications. So if we have a type of oil, say a 10W30 new engine oil, this is straight out of a bottle, and we add debris to it, we can make it very dirty. The machine sees that it's very dirty. It says it's a 232219 ISO cleanliness code, and visually it looks very dirty as well. There's hundreds and hundreds and hundreds of particles visible there, more than you'd want to count. And that oil, and we filter it, we can visually see that we've taken a fair amount of debris out of it. The machine count, however, is staying basically the same. The machine is still saying it's an ISO 232214, but visually we've taken lots of particles out of it. And if we filter it even through a tighter piece of media, the laser machine count is still saying it's an ISO 231914, and visually counted it's down to an 18, 17, 14 or so, or maybe even cleaner than that. The machine continues to read high because it is counting those little gray spheres we saw in the pictures, and it's confusing the machine. It's trying to count the hard particles, but it's counting all that other material that's suspended in the oil along with it. So here's a little additional information on what goes on when people tend to see this. If they see that they did some filtering of an oil and the cleanliness did not improve, they tend to put on tighter and tighter filters to fix the issue, to try and get the ISO count of the fluid down to the target that they're being asked to meet. And when they start over filtering, especially on brand new oils, hydraulic and transmission fluids, a multi-viscosity gear oil like a 10W30, there's two things in there on a new oil that are going to get caught in the filter if you filter tight enough. One of them is the viscosity modifier. For a multi-viscosity oil, new oil with its viscosity modifier in it, you can collect some of that viscosity modifier chemistry in the filter. It hasn't worked its way into the oil. Once it's in service, it works into the fluid and it's basically in there like a liquid. But it's kind of a suspension of a slimy material in the oil when it's brand new, and it can collect in very, very tight filters if you're trying to over filter it. You can see in the top image there's some sort of filming in that scanning electron microscope image in there, and that's filming over with viscosity modifier. Much more familiar is the image down below. The heavily over filtered oil has been loading up with the silicone anti-foam little spheres again. You can see lots of little gray round spheres in that image, and that is the anti-foam additive being filtered out of the fluid because the oil is being filtered far tighter than it should be to get to the kind of ISO cleanliness targets it's supposed to be at. So that this happens routinely at blend plants or incoming delivery into maintenance facilities where they're trying to hit an ISO cleanliness target. Either the oil blender is trying to hit it for the customer, or the customer is trying to ensure that they're putting clean fluids into equipment, and so they're over filtering new oil and collecting these things in the filter. Even though the oil is far cleaner than they need to be, their analytical method with a laser particle counter will lead them to make the decision to filter tighter and tighter and tighter. Again, if we go back to what kind of information you could rely on the report to see that this is going on. Again, it's a new oil analysis, just like before, just kind of covering this again. There are no wear metals, there are no multi-source metals. You still have a really high particle count. Now, those particles should be made of some material, but you have almost nothing on the report other than the additive package materials, which typically don't register as part of a machine particle count, other than the silicone anti-foam that shows up under the contaminant metals section. Again, that's typically in any mobile app. There's almost no mobile fluids that don't contain this material anymore because of high turn rates and smaller reservoir volumes. They're trying to de-aerate the fluids quicker and quicker, and this is the material they have to add to do that. So you'll see it there in many oils, and it will lead you to get a very, very high particle count despite the fluid being very clean. Just again as a reminder, we're talking about tons of these little silicone anti-foam gray spheres. They're in there on purpose. They don't dissolve into the fluid. They float around and break up the air bubbles to keep air leaving the fluid quickly so that they can run these high turn rates on the reservoirs. And they don't damage equipment. The red things circled in red here, the hard particles, are what cause the damage, and you're trying to count those particles to prevent wear and tear in your system. So those are what make up the ISO code. Think of the gray silicone anti-foam here as the fog that you're trying to look through with a laser particle counter, and you can't see the hard particles or the ships that you're actually trying to count, just as a reminder. So there are some solutions that can be applied to limit the effect of this in doing some machine particle counting, but it's always best to visually check, at least initially, to make sure you're getting accurate numbers. And here's an example of that. Filtered visually counted a sample and saw that it was very clean. Got an oil analysis result back saying the oil should have been extremely dirty, and it's not. There aren't a lot of particles in it visually when you're looking. Visually, this was estimated at an ISO 161311 from the image on the right there. The undiluted machine count coming back from the lab was saying it was terribly dirty, 232114, similar to the image on the right, which the oil was not. And you can ask for, and it's becoming a little more common at analysis labs, but they do a 9 or 10-fold dilution with solvent and spread out those small gray spheres, or the small silicone anti-foam spheres. And if they can get them distributed far enough, they can actually just count the hard particles, and it won't count all of those little spheres, and you can get a reasonably accurate count. The same oil sample diluted 10 times produced a machine count that was comparable to the visual estimate. 1613.10 and 1613.11 are essentially the same count. So there are ways around this, but you'd want to test it out visually. It's best practice to make sure you're getting a decent count to know what's going on. Because if you keep putting tighter and tighter filters on and your fluid was already clean, you're just likely to start to plug filters unnecessarily and start stripping that anti-foam unnecessarily out of your oil. So again, just keep in mind that you're looking for hard particles similar to the ship and the distance here, and you're having difficulty getting an accurate number of how many ships are there because there is this suspension of these small particles floating around in the oil, and you're having a hard time seeing the hard particles. They are what does the damage, and they are what you want to assess accurately in your oil analysis. Thank you very much.